In this video, we're going to be talking more about determinants, and I'd like to go over some ways that you can calculate them besides the cofactor expansion that we talked about last time. We're going to be looking at the effect of elementary row and column operations on the determinant first, and then we'll move on and talk about matrix products and scalar multiplication and formulas for inverses and the transpose of a matrix. So let's take a look at some common row operations and see what happens to the determinant. The first row operation that we're going to look at is a row swap. I have a simple example here just to demonstrate, but let's take a 2 by 2 matrix A, B, C, D. Notice that the determinant, just using the determinant formula, is AD minus BC. If we swap the first row and the second row, well, what happens to the determinant? Now it's CB minus AD, or as I've written here, minus AD plus BC. You'll notice that these differ by a sign. So as it turns out, the effect of swapping a pair of rows on the determinant is to change the sign. If you swap a row and then you swap another pair of rows, you'll go back to the original determinant. But you have to be careful about row swaps if you care about the sign of the determinant. Next, let's look at adding a multiple of one row to another. This is the one row operation that has no effect on the determinant. This is just an example to demonstrate, but let's now take something with numbers in it. We're going to look at the matrix 1 minus 3, 2 minus 4. Calculating its determinant, you see that the determinant is 2. If you add 2 times row 1 plus row 2 and put that into row 2, then you get the reduced version of the matrix that you see here. And you can see that the determinant is still 2. Well, this isn't just a coincidence of example. This is a general fact that when you add a multiple of one row to another, you do not change the determinant. So this is a permissible row operation that you can use to simplify your matrix. Notice that in the second matrix, we have something that's actually upper triangular, and so the determinant can be easily calculated as the product down the diagonal, 1 times 2. So this can be a good strategy for calculating a determinant a little bit more quickly. Lastly, let's look at what happens when you scalar multiply a row. This is the row operation that has the most dramatic effect. When you scalar multiply a particular row, it also multiplies the determinant. Let's use the same matrix as our example. And now let's see what happens when we scalar multiply the first row by 7. You can observe in the determinant calculation that that 7 will show up in both of the summons of AD minus BC. So the 7 is also going to be a factor of the entire determinant, 7 times 2. It's not so hard to convince yourself that this is always what happens for a 2 by 2 matrix. If we take a matrix A, B, C, D, and then we multiply either of the rows by, say, X, XA, XB, C, and D, then this new matrix has determinant XA, D, minus XBC, and so you can factor out the X from AD minus BC, which is the determinant of the matrix that you started with. This is true not just for 2 by 2 matrices, but for n by n matrices as well. And what's really happening here is that the determinant is a linear function of rows and a linear function of columns. And it's that linearity property that means that the determinant will be multiplied by the scalar when we scalar multiply a row or a column. We'll be sure to talk more about linearity in the next lecture. But for now, let's continue going through some facts and properties of determinants that you can use to make your calculations more efficient. We have not talked a lot about column operations in this class, so let me just mention in passing that the same thing is true when you apply column operations. So if you do a column swap, the effect on the determinant is going to be to change the sign. And I have a few examples here that you can look at if you're curious about these column operations. Adding a multiple of one column to another will preserve the determinant, and scalar multiplying a column will have the effect of scalar multiplying that determinant as well. So I'd like to now give you a shortcut reminder on some conditions where you know the determinant will be 0. So if you're looking at a matrix and you see that there is an entire row or an entire column of all zeros, you automatically know that the determinant is going to be equal to 0. One of the ways that's easy to check this is to use the cofactor expansion. Similarly, if you see that there are 2 equal rows or 2 equal columns, you're automatically going to have determinant equal to 0 as well. What's happening is the matrix has a linear dependency in it, but since we haven't discussed a linear dependency yet, one thing you can think of is that if you were to do the row operation that corresponded with adding a multiple of one row to another or of one column to another, you could cancel one of the rows, which would then produce an entire row or column of zeros, and then by cofactor expansion, you would see that the determinant is 0. So also, if you see a row that's a multiple of another row, then definitely you're going to have determinant equal to 0. So I have a little quickie example here. 1, 2, 3, 3, 6, 9. These rows are multiples of each other. So performing the basic row operation minus 3 row 1 plus row 2 into row 2 clears out the row and gives you all zeros. And so it's easy to see you're going to get determinant equal to 0. Another convenient fact that we should mention is matrix products. So if you have the product of two matrices, A times B, well, then the determinant of A times B is the determinant of A times the determinant of B. Let's go ahead and jot this down on the next page. All right, so the rule here is in the box. Determinant of AB is determinant A times determinant B. And you can generalize this rule by saying the determinant of a product is the product of the determinants. I have a very short example up here. Let's take as our matrix A, 2, 3, 2, 7. By the 2 by 2 formula, our determinant is 14 minus 6, so that's 8. And our second matrix will be B, 1, 2, 0, 4 with the determinant 4. If you multiply these two matrices together, you can quickly check that you get 216, 232, and then the determinant, of course, works out to be 8 times 4, which is equivalent to 32. This can be really handy. So remember this one. For those of you that are math majors or are interested in proofs, I recommend that you read through the proof of this in the textbook. The basic idea of the proof is that you take your matrix A and you write it as a product of elementary matrices. And then you work out this formula in the event that you have an elementary matrix times, say, some matrix B. And it's pretty straightforward. But for now, we're going to move along and continue talking about different tips and tricks for calculating these determinants. Another important one is how to deal with the scalar multiple of not just a row or a column, but of an entire matrix. So this is different from scalar multiplying a row, although it's related. What do I mean by scalar multiplying a matrix? Well, I mean you're taking a scalar and then you're multiplying it to every entry in the matrix. That's how scalar times matrix is defined. And the rule is, if you have your square matrix A, and C is a scalar, the determinant of CA equals C to the n times the determinant of A. The proof idea for this is that every time you multiply a row by your scalar C, the determinant gets multiplied by C. So if you have n rows, you get C times C times C times C, n times total, giving you C to the n times the determinant of A. Let me just jot down what I said. So one thing to keep in mind is when you see parentheses in these formulas, determinant of CA, as opposed to C times the determinant of A, it's important to notice those details because it really affects the formula. All right, let's look at a little example. Okay, for this little example, we're going to take a upper triangular matrix. And let's look at ABC, 0DE, 00F. A, B, C, D, E, F, these can be any numbers. And we're going to multiply this entire matrix by 7. So the way that scalar multiplication for the matrix works is we're going to have 7A, 7B, 7C, 7 times 0, which is 0, 7D, 7E, 0, 0, and 7F. And now we go to calculate the determinant of this matrix. So the determinant of the original matrix that we start with, by the way, is A, D, F. But 7 times this matrix has determinant 7A times 7D times 7F. And if you consolidate your 7s, you see that this is 7 cubed times ADF. So the effect of multiplying the entire matrix by 7 was to multiply the determinant not by 7 alone, but by 7 cubed, one time for every row. If you ever forget this rule or doubt that you have the formula correct, jot down a simple diagonal or upper triangular matrix and work out what it ought to be in that example. That'll help refresh your memory.